In this video, we're going to give you a sneak peek into a couple of new improvements related to punching shear. These are specific to the ACI code in the software. And we'll go ahead and open a model here and get started. This will be a two-way flat plate that's reinforced. There's no post-tensioning. The same improvements apply to a PT slab also in their implementation. And if we go up here to floor design under shear design options, we have three additional inputs. One is to consider the critical section outside of the shear reinforced zone. And this really relates back to the need to check the stress at a distance d/2 from the last line of reinforcement along the least critical path. Okay, and that critical path being an octagon shape. So to give a little background into how the program has previously checked punching, and we'll go ahead and just draw a sketch here. If we have a column, the program would generate multiple rectilinear sections and check stresses for these sections until there's no additional reinforcement required and until we meet that 2 squared of f prime c check. The change that has been made is when this is selected, what will happen is when the program identifies the last rectilinear section that no longer requires reinforcement, the program will then, and I'm going to add a few rails here just to show this. This is the outcome, let's say, based on rectilinear sections. The program would then go back and it would identify and recheck based on this shape here. And if that particular section did not meet the 2 squared of f prime c, the program develops additional critical sections of the same shape, and it develops those until the stress is less than 2 squared of f prime c, and it adds additional reinforcement and extends the rail. So that's an option that became apparent in the 318.14 code in terms of the verbiage in the code checking the least critical perimeter, and the program now includes that check. You can also see there's this option for edge distance. Just looking at a column again, if we identify this as either a stud rail or a line of vertical shear links or reinforcement, this just identifies this dimension. We'll call this X, and that's needed in order to develop that octagonal shaped critical section. The next improvement that's been made is related to slab and column connections for joints that may not be part of the lateral system. So there's a requirement in high seismic design categories D, E, and F where you need slab shear reinforcement necessary to provide greater than or equal to 3.5 squared of f prime c, and that's for a distance 4 times the slab thickness to each side of the column. So in this case, what we do is we identify the critical sections that extend out to 4 times h. When this option is selected, the program ensures that the reinforcement within this zone exceeds that allowable stress 3.5 squared of f prime c. So this is really just a binary option. It's off or on. There is some wording in the code that if your inner story drift exceeds a value, then you should check this. We essentially ignore that and we just allow the user to turn this off or on. So the user would be required to check that drift and whether or not you actually need, if there's enough side sway and rotation at a joint, you may need to apply this. That's done outside of the program. You can apply this and the program will reinforce for it. So we'll go ahead and look at this in action. I'm going to turn both options off for now, and we're going to run this kind of using legacy coding for ACI318. You'll notice I'm not including uniform spacing, so this is really just the direct result based on the reinforced zones within the periphery around a column. We'll go ahead and we'll look at one of these 4 interior columns. So we're going to analyze. We're going to look at strength dead and live for this example. Once the analysis is complete, I'll go directly and just execute the shear reinforcement check. And under the result browser, I want to check one of the strength combinations to enable the punching shear. And we can see we have required reinforcement on a couple of columns, and there's this exceeds code. That means that at some critical section, we have stresses that exceed, in this case, 6 square root of f prime c. So this identifies that. For these two columns, if we actually go to the reinforcement report, I'll go to the Excel file, we can clearly see for those columns where that occurs. So if I go to the stress check, you can see, for example, at column 4, the stress check is exceeds code. And you see over here, the first critical section didn't pass. The total stress is 0.474, allowable is 0.212. This would actually exceed 6 square root of f prime c because we've decided to use headed studs. So that shows you which critical sections don't pass in that case. Coming back to these columns that we're going to look at, these reinforced, we'll look at column 1 here. The stress ratios can be marked here, and also we'll turn on the condition. It's checking this as a 4-sided critical perimeter. So this is an interior condition versus 3 or 2-sided end, edge, or corner. And then finally, we're going to look at reinforcement. So just looking at some of the reinforcement output, in this case, we have 4 studs at 1.5 inches spacing and 6 at 3. So this is the direct result based on just analyzing every layer. It may not be based on constructability or uniform, kind of normalizing the spacing for different types of rails and arrangements. It's just a direct result. If we go and we look at the report for this result, that will be reflected in the report, just what we see there graphically on screen for column 1, 4 at 1.5, 6 at 3. So we have 10 studs. Now we're going to go back, and if we choose to check the column for those octagonally shaped critical sections, we would expect additional reinforcement because we have a lesser critical section path. We have less area. And you'll notice before we go back and look at that, if we come back to punching shear report, we can see that for column 1, if we look at the design area goes from least to greatest. So it starts to build up and then it stops. And what will happen when we look at the octagonal shape, it will build up and then it will drop because we repeat the check and then we extend out the octagonally shaped section. So let's do that. We'll go to floor design. I'm going to turn on the option for consider critical sections outside the shear reinforced zone. We'll just use a 1-inch spacing for the edge distance, and I'm going to execute the shear again. Remember, we have 10 studs. Now we have 10 plus 11. We have 21 studs in this case. And if we go back to the report, we can see that this is again for column 1. We build up the design area up to section 9, and then it drops. So at section 9, this is where the rectilinear section passes the allowable stress. And again, this is the implementation based on codes ACI318 11 and prior. And then we introduce this octagonally shaped section where we now check the first octagonal section, second, and this actually builds out until we reduce the stress to 2 square root of f prime c. That's actually shown in the stress check. If we look at section 9, this is where the drop occurs. We build up an allowable, and then we drop the allowable to 2 square root of f prime c, and we wait until this stress ratio, or we check until that stress ratio is less than the allowable, and we have a stress check, basically a ratio of 1 or less. And that gives us those additional critical sections. If we look at reinforcement, that's also indicative here. We look at column 1, we can tell there's 0 reinforcement required at section 9, and then we build back up and we check those additional layers, and we have 1 additional stud for each one of those octagonal layers on each rail. So we get a need for more reinforcement because of this check. Now what we'll do is we'll look at the drift check. So I'm going to go ahead and turn off the octagonal check just for a moment. I'll go back to drift check, Looking at our control sample, we said we needed 10 studs. That's kind of the baseline that we're comparing to. If we go back and we execute again, you can see we need 10 and 10. So in the first example, we actually needed 4 at 1.5. Now we need 10 at 1.5 in order to maintain that distance 4 times h. So this is where we get into the need to add studs to control or to meet the requirement for the slab column connections in high seismic zones. So this is an output of 20. Now the worst case, meaning the most reinforcement you would get given the new options here, is if we turn both of these on. So we had 10 and then 21. Now we have 20 without considering the octagonally shaped section. If we recheck this one more time, we have now 20, 26, and 34. And the rail length here is 55 inches. So there's a couple of new options here with respect to punching shear. If you would like any background information on previous implementations or this current implementation, please let us know. You can contact us at support@adaptsoft.com. Thank you.